Good morning, and welcome to Group 1's initial concept presentation for our MEM 435 project. Our group consists of Andrew, Anthony, Barrett, Shane, and me, Emily. After interviewing 2 individuals from Drexel's Academy of Natural Sciences, we decided to model a frog's legs and how it jumps. We strive for our model to be as simple as possible while still giving the students a good understanding of the science behind it and keeping them entertained.
When muscles in the frog's hind leg are contracted, they pull on the tendon, which stores potential energy. When the muscles are relaxed, the stored potential is translated to kinetic energy, which allows the frog to jump. This explains the frog's great jumping capabilities despite the limited muscle size. The distance of the jump is dependent on how much the muscles are contracted, which relates to how much force is applied to the tendon. Our model will demonstrate the impact the force exerted by the frog's hind leg muscles has on the velocity and distance that the frog is able to jump.
The device will be a functional model of a frog's hind legs to demonstrate the interaction between its muscles, tendons, and bone anatomy that allows it to attain the jumps that it does. The footprint of the entire product will be dependent on the base from which the frog legs jump on. This will be approximately a square foot.
Our frog leg model will be made up of 4 bones made of aluminum attached with 5 pins. Toes will be fastened to the lowest bone, and the pelvis will be contained by a plastic frog's body so that it is readily apparent to the students what is being modeled. Elastic bands will be placed on the outside of the pins attached to the leg bones. When the model is compressed, the elastic will stretch, building potential energy. When the leg model is released, it will jump into its extended state, translating the potential energy into motion and applying a force that will output a distance that the frog achieved on a gauge. This will keep the model simple and safer by mechanically preventing the model from jumping off of the base, but outputting what distance it would achieve still gives students interesting information that they can see how the input affects the output, as well as potentially make it a game with their friends. A fishing line is aligned along the leg lengths, and when it is pulled, the model is compressed. To adjust the applied force, a lever controls a brake pad, dampening the effects of the release when a lower force is set. This will allow for the full contraction of the legs each time, like real frogs do, but then they release their tendons at different rates to adjust their jumps. This will mimic that in a simple mechanical way.
To actuate the device, the customer will pull back on a horizontal lever, compressing the frog's legs. The force in which the frog will jump with will then be adjusted by a vertical lever. This will control the reaction speed and force of the muscles to show how the same motion every time can achieve different jumps, just like actual frogs. This will also allow the jump to be run very slowly if desired, to give the students a slow motion view of the biomechanics of a frog's legs.
The design covers relevant and important topics discussed with the museum and their goals for an upcoming exhibit, while also demonstrating applied science topics about force and simple machine concepts using springs and lever systems. The setup should take less than a minute, and none of the product's movements will pose any risk to the operator or students. This concept we have has not yet been seen on the market. Frogs are fragile, and it is difficult to show how they jump using a live frog. In speaking with the museum, they have not seen this kind of model before and think it'll be very useful for an upcoming exhibit about frogs.